You in the last row, can you hear me? Okay. Can you understand me? Good. Everyone who is married knows that there is a difference between hearing and understanding. Thank you for inviting me. Thank you for having me here again. I was here, I don't know exactly, probably 10 years ago. We were in the other building there on the other side. Was it 10 years probably, or 12, something like that? And I think it was in winter as well. It was cold, I think, when I remember. Okay. So sometimes, always when I'm in the Netherlands, it's cold. Jan Willem told me I have 5 hours time, so until tonight, so for dinner. So I prepared 860 slides, and so I tried to explain to you everything what I learned in the last 35 years from you. No, I'm kidding. Yeah, you can if you want. So I'm not yet sure what I should talk about. So do you have any idea? No? Trees? Good idea. Who in this hall is inspecting trees on a daily basis? Okay. Who does it with some technology, some kind of machine, drilling or sounding? Oh, there are a few. Okay. Who does tree inspection sometimes? So some evaluation? Okay, probably nearly all of you. So there's probably no one in the room that is never in contact to any kind of tree inspection and evaluation. That's good. So it makes sense that I'm here. So I'll try to, and again, I will talk in English. Probably not the best English, but I'll try to be clear enough. When something is not clear, please immediately ask questions. So when something is not clear, please immediately raise your hand and ask questions. Otherwise, you could get lost over the tour of the presentation. What I will show you here, you will receive a link online. You can revisit all these slides. So if you want, you can take pictures, but you don't need to. That means afterwards you can always revisit that, the PDFs that we show here. And I would like to come back a little bit in the history of tree inspection. Who in the room knows Alex Scheigo? Who met Alex? Okay. Oh, several people met Alex Scheigo. That's great. Okay, so his first lecture in Europe was 1984 in Heidelberg. And he basically destroyed tree surgery with this lecture. And when he wanted to leave the room, he needed a bulletproof vest. Probably you know that, because at that time we had a few quite big companies, and it was big business, pruning trees and taking all the dirt away, putting concrete in, and a lot of chemicals. It was really big business for many years. And Scheigo started basically the transformation of that industry into a more modern, more science-based industry. And I started studying physics in 1982. Before I worked as a carpenter, so I was a bit used to working with wood because my family has a sawmill and a carpentry and a farm, so I was used a bit working outside. And then I studied physics, and in the Institute of Environmental Physics of Heidelberg University in 1986, someone called and said, we have a question, is it possible to drill in a tree with a thin stick needle, with a thin needle like that? I'll pass it around, so please don't stick your neighbor, but the question was, is it possible to drill a tree with that? The question came from the University of Hohenheim, which is south of Stuttgart, and they had a special institute called dendrochronology, so tree ring dating, tree ring analysis. And they got a request from a company, actually, that is manufacturing battery-driven drills, Fine, in Stuttgart. They provide orange machines, so typically the color is orange of these machines. And Mr. Fine had invented the first electrical drill in 1880 something, so a very innovative company in Stuttgart, still existing. And they got a request if they could build a hand-driven drill to drill in trees and in utility poles or timber to find out if there is decay inside or not. That was the request. And they asked the University of Hohenheim with this institute of tree ring dating, dendrochronology, because they were experts in wood, in timber. And so the botanist said, sure, we will do that, but they had no clue about technology, so they called Heidelberg University. And Heidelberg University, I was studying there, they said, Frank, would you like to do that? And I said, yes. So I moved to Stuttgart, and my challenge was take a thin needle, stick it into wood, and try to get something out. That was the idea. And as you can all imagine, this was the birth time of the resistance drilling for tree inspection. So when I did that, sorry, it was 1986, and immediately after the first publications, I got phone calls from all over the world, and people said, hey, we need this machine because we need to know if a tree is decayed inside. So we need this machine, so we sold the first machines, and within a few months, people called me back and said, okay, now we know the tree is hollow or decayed, but what does it mean in terms of breakage safety? So we know the tree is hollow, but is it stable or not? So that means we had a solution for a technical problem, and the machine worked quite well. So you see the machine there. It was a orange machine, and there were a lot of news coverage, TV shows, and so on. And we found profiles that showed tree rings and if the tree is decayed or not. But it didn't answer the question, is the tree stable or not? And so people said, oh yeah, Frank, you sold us the great machine, but can you tell us when the tree is not anymore stable enough? And I said, no, I can't. And in 1991, so 5 years after this first development, I got a phone call from the Nuclear Research Center in Karlsruhe, and Professor Munz, the director of the Institute of Failure Mechanics in Engineering, he asked me to come, and he said, Mr. Rinn, we found your publication that's interesting because we can study the internal structure of trees. In my institute, I have a department, and the department head, he should optimize mechanical structures for power plants, for any kind of mechanical stuff. And would you please explain this guy how to drill trees and how to inspect trees? And can you imagine the name of that guy that was working there? Yeah, it was Klaus Matek, yeah. So I came there, I met that crazy guy, and I had to, who knows him personally? Who met Klaus Matek personally yet? Oh, few. Okay, the other ones, if you have a chance, meet him. Go to a meeting of him, a presentation. It's really interesting and challenging at the same time. So, or you can go on YouTube and check some YouTube videos. It's interesting. You can learn a lot from him. So my challenge was to explain him how to drill trees, and we did that. We did a lot of trees drilling together, starting in 1991. And what was the result? 2 years later, Klaus said, I have the solution. To evaluate if a tree is safe or not, we just drill into the tree, and in the profile of the drilling, we determine the thickness of the intact shell wall, thickness, and this is why the word, the character T is used, T, thickness, and we divide it by the radius R, and the ratio should be above 1/3, and then the tree is safe. And he said it should be simple, so everyone should be able to apply that. So very simple. He said we just drill between the buttresses, and he published this frequently again and again. So to assess the T over R 1/3 rule, drill between the buttresses where the shell wall is the thinnest, and with the T over R ratio, you can evaluate if the tree is safe or not. And I don't know if some of you can remember what happened at that time. This publication showing this graph where the broken trees are shown with a black square and the intact trees are shown with a hollow circle, there is no broken tree above the 1/3 line. What indicates it is absolute safety up there. And especially lawyers, judges, so people from outside the green area, they had been absolutely happy with it. Because until that point, in many court cases, people had been having very different opinions about trees. Yeah? The one expert said it's obviously that the tree was safe enough, and the other expert said it was obvious that the tree was not safe enough, based on experience or whatever. And what did the judges typically do? The judges are lawyers, typically educated in legal stuff and not in engineering. So the judges typically had no idea what's the science behind all that. So typically the judges said, okay, the person, the expert with the highest academic degree, he will most likely be the correct one. So typically in court cases about trees, when something happened with an accident, the judges followed the person, the expert with the highest academic degree. And with this graph, for the first time, there was a allegedly absolute clear number to check if the tree is safe or not. And because there is no broken tree shown above the 1/3 line, yeah, you can see in that graph, there is no broken tree represented by a black square above the 1/3 line, the people said, oh, that's great, we have practically absolute safety above there. So this publication came from an official federal research institution, from a German professor, so it must be correct. And the consequence was that this was the base for decisions on trees within a few weeks worldwide. So in consequence, tens of thousands of resistance drills were sold, and people started drilling trees like crazy, because the advice was, drill your trees annually, check the T/R value, and if it's above 1/3, you're fine. If it's below 1/3, you have to either prune the tree or cut it down. And this started to happen in 1993. So it was an exponential growth. It was like crazy, and you couldn't imagine that worldwide. And I remember approximately more than 50 countries adapted this rule. And a lot of them even put it into national standards. We had cities at that time that made contracts with insurance companies about damages, potential damages with trees, and in the contract it was specified the city has to drill every tree once per year from the street side to check the T/R ratio, and as long as the city does it, the insurance will cover all the damages if something happens. So this drove the market, and this graph, the combination of all that stuff, was the main reason for the success of VTA. Yeah, because it divided the world into two pieces, a safe area and a potentially unsafe area. And that made life so easy for lawyers and judges and other people that had no clue about trees, because they just asked for this value and then the case was over. So the driving factor for the success of that concept was more coming from outside of tree business than from inside, because I knew at that time already a lot of people from municipalities that were experienced with trees, and they knew exactly that's not right. But the driving factor was coming from outside, from other factors. So, and that explains the huge success of that method. So, but in reality, I think you all know that. When you observe nature, you will find easily many, many trees that break, although the T/R value is above 1/3. So interestingly, they don't show up in this graph. So the blue dots here are just examples from trees that broke, city trees, and the T/R ratio was above 1/3. They had just not been shown in the statistics. They were just taken out, that's all. Yeah, very simple. When you do that, over the years, you find out there is no clear line between safe and unsafe. It's a gradual development. If this would have been published, this is a more correct result because it covers more of the data. This would never have been successful because it doesn't distinguish between safe and unsafe. And then the judges, the lawyers, insurance companies, they would have not taken into account that this is somehow valuable. So this would not have made VTA successful. So the key factor that VTA was successful and this T/R ratio was so and is still so largely used worldwide, the key point is the fact that here there's no value above the 1/3 line that broke. That's the key point. Another reason that came into point, and this is important to understand. When you check the typical cross-sections of urban trees, they are fundamentally different from trees that are standing in the forest. And the first trees that were drilled by Klaus Mattek with me, because I was the one who drilled it, were always trees in the forest. It was not urban trees. In forest trees, the cross-sections are mostly quite circular and the decay is in the center. But in the urban trees, the decay mostly is not in the center and the cross-sections are mostly not concentric. And as soon as the cross-section is not concentric and as soon as the decay is not in the center, the T/R shell wall ratio doesn't mean anything about stability of that cross-section. Yeah, that means it's important to understand the T/R ratio is not wrong. The T/R rule, 1/3, is not wrong, but it is only applicable to a very specific kind of tree and not to the trees that we are typically inspecting and that we have to evaluate. In addition, when you drill between the buttresses, what happens when you drill between the buttresses? The needle is in the bark, in the included bark. And I don't know if you remember that. I don't know how many people have already been in this field in the early 1990s. Thousands of trees had been cut down or felled because people drilled between the buttresses in urban trees. In the profile, they didn't find any significant amount of wood, because they drilled into the bark, and then cut the tree down. And this happened thousands of times. It still happens. It still just happened in Montreal in Toronto, in Canada. Just a huge, magnificent tree was cut down just because of the included bark effect that was not taken into account. So that means drilling between the buttresses in urban trees is wrong. Especially when you use a very modern kind of resistance drill that has a so-called automatic void detection. When you drill into this cross-section here, here, I'll go here, front. So when you drill in here, you have about 5 centimeters of wood, and then you have included bark. That means the profile is up, and then it drops down because the needle goes into the included bark, and it looks like being decayed because there's no resistance anymore in the included bark. And the same happens in the different points here when you do it here and there and here, and then you say, okay, I drilled this tree 3 times. After 5 or 6 centimeters, there's no resistance anymore. Cut it down. That's the reason why this tree was cut down. And that's not the only tree. Thousands of trees are cut down because of that. So that means, generally speaking, drilling between the buttresses does not make any sense in urban trees. The typical mature urban trees that we have to inspect in terms of safety and to evaluate, they are different. When we have to drill in these trees, we have to drill into the buttresses and not between. Never between the buttresses. So the advice that was given at the early beginning, here, drilling between the buttresses, it's correct for forest trees, for slender spruce trees in the forest, but these are not the trees that we are inspecting in the urban environment. So that means the advice drilling between the buttress and measuring the T/R is not wrong, but it is only applicable to a kind of wood or tree that we typically don't inspect. So another aspect is important when evaluating. Actually, this was the reason why I developed the sonic tomography, because I thought it's so crazy to condemn trees just by 1 or 2 drillings. So we need a method that allows us to show the whole cross-section of the tree. So because of the frustration about this wrong application of this technology, I thought we need a method that shows a tomographic picture. And so we started developing sonic tomography in the early 1990s. And it was patented in 1999, showing the whole cross-section as a colored picture. Another point is important to understand what happened to VTA and the T/R rule over the years. What I just already mentioned, as soon as the cross-sections are not circular and as soon as the decay is not in the center, the T/R ratio does not represent the load-carrying capacity of that cross-section. You can imagine, for example, this here is a pine tree in the city where you see the sidewalk, they cut off the roots because of the sidewalk building, and then the decay came from that root into that stem. The T/R ratio is very small here, better here, very good here. So in the one section, you can have 100 different kinds of T/R ratios. That means there is no one T/R ratio that represents the load carrying capacity of that cross section. And the same up here with that spruce, the beech here, the beech down there, so, or the horse chestnut in the center. Forget it. T/R ratios don't make sense as soon as the shell wall is not homogeneous around the cross section. And this is only happening in forests with a circular stem with a centrally rotten zone. So in the real world of urban trees, this ratio doesn't make any sense. In addition, there is an aspect that has to be taken into account that had been ignored by VTA, yet still today. This is an example of old trees. Old oak trees, approximately 120 years old. They are standing in a park at the beach in Miami. So Miami, you probably remember, Miami is a city where approximately 5 to 7 hurricanes come in from the seaside every year, with wind speeds typically 100 kilometers per hour. A few months earlier than I was there was a storm with 250 kilometers per hour wind speed. 250 kilometers. I think you don't go out of the house at this high wind speed. At one day I was there, while such a storm came in, you stay at home. I mean, you can. Yeah, it's really bad. And the gardening guy of that park, he called me and said if I could check these trees, because he said he tapped on the trees and he found that they are hollow. And he said, that's dangerous. When a tree is hollow, it's dangerous. So I came to that park, beautiful, magnificent park. The building here, you see there, was built 1890 or something like that. And the shoreline is directly beside the building. So these old trees, southern white oak, typically 15, 17, 18 meters tall. These oak trees are approximately 120 years old. That means they survived a few hundred hurricanes with high wind speeds. And a few months earlier, before I was there was a hurricane with more than 200 kilometers per hour wind speed. So I asked the gardening guy, how many of these old hollow trees snapped, failed, broke in that storm? And he said, none. And I said, what happened in that storm? And he said, oh, we lost many trees. And I said, yeah, which kind of trees did you lose? And he said, oh, the young ones, the intact ones. And I said, okay, do I still need to inspect the old ones? And he said, well, probably not. Yeah, this is a nice example showing that an old hollow tree can be safer than a young intact tree. And this explains that the safety factor of trees changes over time. That means older trees, yeah.
Is that because hollow trees are more flexible?
No, it's the opposite.
The width is...
No, sorry.
It's the width.
No. It's a very simple thing.
Can you repeat the questions?
I repeat the question. I get the same question often, so thank you for that, and you're not alone with that questions. It's often said that a hollow structure is stronger than a solid structure. I think you all often hear that. That is wrong. The comparison that explains that hollow structures have advantages comes from mechanical engineering. When you have 1 kilogram of aluminum and you have to support, let's say, a 1 meter long thing, then with 1 kilogram of aluminum you can make a thin rod, or you can make a tube with a thin shell wall, and then the tube carries more load than the thin solid rod. That means when you have the same amount of material, then a solid rock and a small solid rod is weaker than a hollow tube with the same amount of material. But a hollow tree is safer because of other reasons, and I will explain them afterwards. So it's not flexibility, it's not stiffness, it's a totally other different effect. And afterwards you will immediately realize it's a very simple thing. Next example. The sequoia trees, all the ones shown here are more than 60 meters tall. One of them is 83, bottom right, 83. And obviously these trees don't read literature. So they just ignore the 1/3 rule. Some of these trees are about 600 years old. One is about 800 years. The one probably 1,000-year-old. So, and several trees of these sequoia trees are hollow since more than 100 years. So I saw pictures of these trees 100 years ago when people sat in the tree, in the void, playing cards and drinking whatever stuff. So that means since 100 years at least, these trees ignore the 1/3 rule. And the cross-sections look like this down there. Yeah, 90% of the cross-section is gone, and there is some intact wood on the outside. That's it. And this is with trees that are 60, 70, 80 meters tall, and several of them have even been clear-cutted around. That means this tree here, where you can go through with your car and you pay $3. That's my youngest son. He goes through, and he's 1.90 meters, so it's really a big void in it. So you can go through. This tree was really standing in the forest, and then the owner took down all the other trees around it. He said, then we can better see that tree. He didn't realize that this increases the wind load, but the tree still ignores that. Yeah? So that means old trees can be extremely hollow and still obviously safe enough. And the nicest example, this is an old oak tree, a very big one, standing in front of Windsor Castle in England. And the Queen used to ride with her horse around that tree. She loved it. So I was there a few years ago to give a training. And in 1987, this tree survived as one of the few ones in this field, this extreme strong hurricane in southern England where millions of trees snapped. So from far away, I thought this must be a strong tree. That's the stem. Please drill between the buttresses and tell me the T/R ratio. Somehow it seems to be 0. It is 0, yeah. So summarizing, and that's an important point that I would like to make sure that you understand it. The T/R ratio is not wrong. The T/R ratio correctly describes that the breakage probability of hollow trees increases as soon as the shell wall gets thinner than 1/3 of the radius. This is totally correct, but it is only applicable and only valid for trees that are still growing in height, not old trees, still growing in height, having a circular cross-section and having a centrally rotten zone. Only when these 3 conditions are met, then the 1/3 rule is valid. For all other trees, it's not valid, but it's not wrong. Because often you can find publications and you can hear a lot of presentations that the T/R ratio is wrong. No, it's not wrong. It is correct. It is scientifically proven correct, but it is only valid for a very specific kind of tree that we usually never inspect. So we can learn from it, but we should never use it. Yeah, that's the important point. So what's the consequence of it? Unfortunately, we had some good and many bad consequences of that T/R ratio. First of all, in 1994, Steffen Wiebe, a German tree expert living close to Munich in Augsburg, he said, we need to stop that crazy cutting down trees because of drilling between the buttresses. And we need to sit together and to think about a strategy to stop VTA. Because one other aspect was that when the T/R ratio was shown, the judges typically on these big conferences in Germany said, okay, as soon as there is any kind of a fungus at the tree, so a symptom that something might be wrong, you have to at least do something at the tree. And the something was typically cut down 1/3 of the crown or 1/2 of it to reduce the wind load. Or if it's a beech, just take down the whole tree and replace it. Because why should we invest in old trees that have a defect already when for the same money we can plant 2 or 3 new trees? So that was the argument at that time. And to stop that, Steffen Wiebe said, okay, everyone who hates Klaus Mattek will come to Augsburg at the same time when Mattek has his conference in Karlsruhe. And that was the birth time of the Augsburg Tree Care meeting, Augsburger Baumpflegetage, probably you know that. Who has been in Augsburg already on that conference? Okay, several of you, yeah. So the meeting in Augsburg was designed in 1994 with the goal, with the explicit goal, everyone who doesn't like VTA and the drilling and Klaus-Matek, he can and should come to Augsburg, meet together. And the condition to give a lecture there is that you in the public say that you don't like Klaus-Matek and you don't like VTA and you don't like drilling. So, and this is still the same today. Until today, in the Augsburg tree care meeting, there was never ever a lecture on resistance drilling, because resistance drilling was seen as a bad thing, because it kills trees. Because the application of the drilling in the wrong way, that means the application drilling between the buttresses as clearly advised in these publications, drilling between the buttresses, this was the birth time of the catchphrase, drilling kills trees. So that means the catchphrase, drilling kills trees, was not because of the drilling, but because drilling between the buttresses and then drawing the wrong conclusions from that. It was not the drilling itself. Until today, we never found any tree where there was any kind of significant decay in the drilling hole. And we drilled millions of trees since 1986. And we opened a lot of these trees afterwards, after 10 years, 20 years, or 30 years. And never ever in any kind of drilling hole we found any kind of decay. Most likely that's the consequence of the heat during the drilling. During drilling, in the drilling hole, the temperature goes up to several hundred degrees. In several trees, the shavings are burning to ash. That means the internal structure in the drilling hole is carbonized. And when you carbonize wood, typically fungi don't like it anymore. So that means the drilling itself doesn't harm the tree. What was killing the tree was the wrong conclusion from the wrong drilling. It was not the drilling itself that did the wrong thing. So that the catchphrase drilling kills trees comes from the wrong drilling kind, not the drilling itself. Okay, so one of the main consequences, as I mentioned, was people started looking for an alternative. So we need something that stops VTA from cutting down so many trees. Unfortunately, in these early 1990s, the judges, the courts, the insurance companies, they all loved VTA because of that clear graph and the clear decision, the easy way of deciding if a tree is safe or not. And so the people that wanted to stop that were looking for a scientist that was capable providing a theory that allows to have an alternative to VTA. It needed to have a scientific background, so it should come from a university. And it needed to be a bit complex so that it looks scientifically and difficult. And they found it. And it's called SIA. Who in the room does not know SIA? Static Integrated Assessment, you all know it. Okay, so that's good. You're all familiar with that. So the success of SIA is largely a consequence of the extreme and dogmatic application of the VTA. The SIA concept came in conjunction with the concept of pulling tests. I think you all know pulling tests, or is there anyone who does not know pulling tests? You all know that, okay, That means you pull on the tree, you measure strain and inclination, and you conclude on the uprooting safety and the breakage safety. And in conjunction with the pulling test and the theory of SIA, Steffen Wiebe and his friends in Augsburg tried to establish this method as an alternative to VTA. And so this is why in Augsburg more and more people came together and tried to establish and to set that up to a kind of, let's say, a standard. And they were quite successful. Within a few years, they achieved that the German standardization organization, the FLL in Bonn, they took over the SIA concept and put it into the standard. One aspect of that SIA concept was the so-called dynamic crown cabling. I think you are all familiar with dynamic crown cabling, Cobra cables or so. You know that? Anyone here who does not know the cables? Is it a standard practice in Netherlands? Yeah? I would recommend you to stop that. It doesn't work. And I hope in that lecture that I can explain you why it came up. It did not come up because it was a scientifically proven method. It was just a psychological treatment of the people that are responsible for the trees. It was not introduced to damp movement in trees and to save trees. It was introduced to keep people away from topping trees. That was the main reason behind the dynamic crown cable, especially as an alternative to the static cabling that is done more at the base of the tree. So that means the dynamic crown cabling was part of that whole concept, and it looked scientifically grounded because the SIA, the Static Integrated Assessment, basically says we apply to trees what we apply in structural buildings. Like when you design a building like that, you have your standard steel profiles that you set up there, and in this case it's quite easy. You know the maximum potential snow load that will be on such a roof is, for example, 100 tons, and then the roof has to be, depending on your standard, strong enough for 150 tons. Yeah, so the roof has to be stronger than the maximum load that is expected to happen. And in most countries in Europe, we have a clear standard saying, okay, when the maximum load is 100 tons, then the load carrying capacity should be 150 tons or 200 tons. When it would be 200 tons, the maximum load carrying capacity, and the maximum load would be 100 ton, then the safety factor would be 2. Yeah, because the load carrying capacity is twice as much as the load. And the safety factor is very simply determined by just dividing the load carrying capacity by the load. So when, for example, that structure here is a mechanical structure, when it can carry 500 tons, 500 kilogram, and the normal load that typically comes up is, let's say, 200 kilogram, then the safety factor is 2.5. So it's very simple calculation. And Vesely was educated as an engineer in Stuttgart University for calculating and designing aluminum structures for solar panels. So he applied the equations that he learned for aluminum structures to trees. And he said, very simple, we take a picture of the tree, we assume a wind speed. This allows us to determine the wind load. And by knowing the material properties of wood, we can calculate the load carrying capacity of a tree. Then we divide the two values, and this gives us the safety value of a tree. It's very simple. It's simple when you write it down this way. When you look in reality, it gets a bit more difficult. These are 9 trees standing close to Stuttgart, funnily close to Stuttgart, south of Stuttgart. The 9 trees have different heights, but the height over diameter ratio, so height divided by diameter, is approximately 60 for all these trees. I forgot to mention that VTA, in addition to the T over R 1/3 rule, has another so-called rule or safety measure, and it was published various times in German and English language, that the height over diameter ratio of trees should be below 50. Yeah, that means you measure the height of a tree, let's say with an inclinometer, a laser device or whatever, or you climb up when you want to be precise, and then you take a caliper and you measure the diameter of the tree, and you divide the height over diameter, and the result is height over diameter ratio, and this should be below 50 for ensuring sufficient safety of that tree. So these 9 trees are standing on a hill. As you see, there is no wind protection. The houses are much deeper. So these trees, poplar trees, are standing in full winds since about approximately 45 years. And the VTA-trained expert says these trees are dangerous because the height over diameter ratio is above 50. So these trees are too slender. And the recommendation of the VTA expert is top the trees or cut it down. The owner said, no, because I want to keep the trees. So I'll ask another expert. And the other expert is an SIA-trained expert. So what does the SIA-trained expert do? He put the values of these trees in the SIA form that is freely available online, doesn't cost money, just free of charge. You select the tree species, you give in the height of the tree, the diameter of the trunk, and the thickness of the bark, and the form online shows you, the safety of these trees is only 0.27%, 27%, so 0.27. That actually means the trees are about a factor of 5 too weak. And what is the consequence? The consequence is that worldwide thousands of trees are felled since these things are public. I was just in England on a university, and they just cut down a whole row of poplar trees. And I asked them, why did you do that? And they said, yeah, very simple. The height over diameter ratio was more than 50. The SIA said, people said, oh, VTA is wrong, that ratio doesn't make sense. Let's put the values of these trees into that form. And the form resulted in, oh shit, the safety value is below 0, so we have to do something. So they cut down these trees. Because when you keep these trees, although the two major worldwide accepted and known methods to evaluate trees, when these two methods tell you the trees are not safe enough, and one of these trees snaps down and kills someone, you will be in trouble. In a German city, the gardening director, he's a very good, very well-trained guy. He had an expert report from a professor from university, and this professor said, you have about 5,800 beech trees, intact trees, and they have a height over diameter ratio that is above 50. They are too slender, you have to cut them down. They are too dangerous. And when you then put these values of these trees into that form, and SIA tells you the trees are not safe enough, what do you do as the responsible person in the administration?
Does the SIA forum take into account whether they are standing in the forest or...
Yes, yes. In the form you put in if they are standing countryside, wind exposed, or in the city. It takes into account that point. And even the distance to the neighboring trees is taken into account. I don't blame anyone cutting down these trees because it's very difficult to defend keeping these trees up. Because when one of these trees falls down, you are responsible. And in Germany, I don't know if that's the same in the Netherlands. In Germany, the people that are working in the municipality are responsible personally. If a tree cracks down and kills someone, it's not the municipality that has to pay the damage, but the person that was responsible for the tree personally is responsible, and he's in charge in the court case. In Augsburg, unfortunately, last year, a child was killed on a playground by a tree, and the employed tree inspector by the city, employed, working for the city, he got punished a few weeks ago in the court. So the people working in the cities responsible for the inspection are personally liable. It's not the city that takes the responsibility, it's the person in the municipality. And that's the reason why in Germany this happens. And this happens worldwide. As I said, just in England, they cut down a whole alley of intact trees without any decay, because they said the two major methods tell us these trees are too dangerous. How can we defend this if something happens with these trees? We can't. So get rid of these trees, cut it down. Intact trees are cut down like this. And this happens every day. Because measuring height over diameter is simple. You don't need any tool for that, yeah? Height over diameter is so simple. Just do it quick. In a minute you know the values. And then online with your smartphone you can check if SIA has the same opinion about the tree. Yeah, and then decide. Ignorance is not doesn't help a lot because you know what happens, so you have to do something. And the consequence is that worldwide trees are cut down because of these two theories being completely wrong. Because I think it's obvious, when these 9 trees would have a safety factor of 0.27, they would not exist. Because it means that the wind is 4 times stronger than the load carrying capacity. If this would be the case, such kind of trees just would not exist on Earth. So the theory is just completely wrong. Another example, an old tree, was a question? Oh, sorry, I missed that.
One weak point of the website is that you cannot fill in a wind area. Like in the west of the Netherlands, you have a different wind speed than in the east, and in Germany it will be even less. But you cannot use
yet on the website.
That's right. Yeah. This is, yeah, the question was, can you adapt it to different wind locations? No, you can't. You can say it's wind exposed, but you cannot say it's in the coastline, for example. Yeah. So this is another reason for why I'm explaining that this doesn't make sense to use it. It's just wrong. Yeah. And we know, yeah, we know why it's wrong. Just another example, and then we have a short break. This is an old oak tree standing close to Cleveland in Ohio, United States. You can probably see there are some small people down there, not small people, but interesting people, but they look quite small because the tree is so big. It's an old oak tree. The lady that owned the tree asked me if I could inspect it because she said, this tree is not allowed to go before I die. She was probably 83 years old or so. And you can imagine what the VTA guys said to that tree. Because when you drill between the buttresses, the shell wall is like that. And the VTA trained people said, cut the tree down. And the old lady said, no, I want to keep that tree because he should be alive as long as I'm alive, at least. So asking SIA experts about the same tree, put these values of that tree into that form, and the SIA form tells you the safety factor is 5,679%, and the tree needs a shell wall of 1 centimeter to stand up. I inspected several thousand, 10,000s of trees since 1986, and I never found a tree with 25 meters height, 2.50 meters diameter that is standing on a 1 centimeter shell wall. Probably it doesn't exist. So that shows this method is fundamentally wrong. And what means fundamentally wrong, I would like to explain a little bit, because often people don't get that. The value here is wrong by about a factor of 15. A factor of 15. What means a factor of 15? You are standing in front of a tree and the tree is 10 meters in height. And you have to note that in your report about the tree, height of the tree. And you don't write 10 meters, but 150 meters. This is wrong by a factor of 15. Yeah? It's not a bit wrong. It is just fundamentally wrong. And it's so obvious why it's wrong, because Vesely just used the wrong mathematics. He used equations that are used for calculating aluminum tubes, thick-walled aluminum tubes. And wood is a little bit different from aluminum, at least a bit. And everyone who is working on wood knows that immediately when he's working with his hands on wood. You feel that. Working with aluminum is another kind of work than working with wood. So that means all these methods that are available on the market are just fundamentally wrong when we deal with trees that are standing in the urban environment. That means when we deal with mature urban trees where it makes sense to keep them, we need something else. And after a short break, I will show you how we should do that. Okay, we had some interesting discussions in the breaks. And I was standing in front of the heater because I got freezing cold here in front. I think you realized I was quite quick in many ways, and I'm sorry for that. Probably not everything was clear. So I would suggest if you're interested in learning more about it, just visit, no, not our website, but no, you will be provided. I think we will send Jan Willem a link, and then you can revisit all that stuff that I'm showing you, what I showed you before. In addition, we started recording stuff in Heidelberg where I explain that stuff in more proper English than today, and then sometimes even in German. So I would just like to mention a few aspects that we were talking about in the break to explain aspects that I mentioned before, just roughly. The main problem of the SIA concept, and again, it was a good idea, and it was, is it loud enough? Loud enough? Yeah? Okay. So the main idea behind the SIA is based on engineering, on established standards. It's really working. But it's not working for trees. And it's not working for trees because trees are so much more complex than our mechanical structures. Calculating such a roof here is much easier than calculating a tree. And that's really important for you to understand. When an engineer comes and tells you he's able to calculate a tree, mostly he's not right because he doesn't understand the tree. Calculating structures like this is completely simple compared to trees. And one reason is shown here on these graphs. These are vertical cuts through stems of trees. On the right, the three are eucalypt trees, very similar to beech or any kind of diffuse porous trees like poplar, tilia. On the left, it's Pinus radiata, the typical fast-growing conifer tree that is grown in Australia and in New Zealand. And just a few aspects of it that I would like to show. Is it okay to step up? Yeah. Okay, so density. Yeah, so that's a cut through the whole stem, and it clearly shows the density is low, blue is low, high is red. The density is low in the center, all up the stem. So the center part of conifer trees typically is quite soft. When the trees get older, the density goes up. That means the strength of the wood goes up. Especially urban trees, when conifer trees are standing because of soil compaction, any kind of stress that is in the city, the consequence typically is that the wood gets stronger. And the wood on the perimeter at the outer edge of the stem can be twice as strong as the wood in the center of the same tree. Sometimes even 3 times. Yeah, that means you have huge changes in material properties within the trees, depending on the boundary conditions, depending on climate, depending on the soil, depending on all the other conditions that they have. That means the tree is continuously adapting these material properties. Conifer trees are, compared to diffuse porous trees, quite simple because typically they are always soft in the center, except very few exceptions, a few in the Alps, for example. But typically the trees are very soft in the center, and the older they get, the higher the density of the outermost wood. When you go up the tree, and every climber knows that, the wood gets more soft and it's more flexible. The reason for the flexibility is one, the density, and the other one is the fiber angle, the angle of the cellulose fibers in the cell wall. This determines the stiffness of the wood largely. It's not directly depending on the density, so the combination of the fiber angle and the density, this determines the material property of the trees. In conifers, as I mentioned, typically it's quite simple and it's quite the same for all conifer trees. You find the same plot in Northern America, the same in Siberia, the same in Australia, the same in Southern America and in Europe, everywhere. So the typical structure of these trees, of the stems, is the same. Windows goes to sleep. I hate Windows, they know that. Okay, here we are. In diffuse porous trees, it's a bit more complex because they change the density and they change the fiber angle. That means the density in the center is quite small at the base. When you go up the stem, the density increases. So it's the opposite from what happens in conifer trees. It increases in the center and it increases especially outside. As soon as big limbs, big branches go out the stem, the tree needs to build up high density wood in order to compensate that static constant loading. And this leads to the fact that the density up here can be twice as high as down here at the same tree. In addition, the tree changes the fiber angle in the cell wall. And this is here, the fiber angle is very low, very high in the center, very low in the outer perimeter of the stem. And the combination of the low fiber angle and the high density leads to the fact that the wood outside here is extremely strong, and compared to the center, it can be 10 times stronger. In the same tree, you can have differences in material properties by a factor of 10. But when you calculate, yeah, there's a question?
What did you measure it with?
This is, I didn't measure it. I would love having been able to do that. It was measured with a machine, Sylvi-Scan, costs about 20 million. And this is an X-ray machine that is able to measure down to 1 micron precision the material properties of wood. It was developed at Melbourne University for the pulp and paper industry because they wanted to know which wood species grow the best wood on which soil, depending on species and whatever, forest operations, for producing pulp and paper. And as a side effect, so this was done in the 1990s. As a side effect, we found out that this helps us understanding the biomechanics of trees. So this study was not done for studying biomechanics, it was just a side effect on that. Yeah? So it was Rob Evans in Melbourne who did that. So probably I have to operate this every 10 seconds so that it doesn't go to sleep. Yeah, another?
Microfibril angle, what do you mean by that?
That's this. The green represents the tracheids, the wooden cell, and this angle between this is the vertical axis where the water flows in the tree, the vertical axis of the tree, and that's the cell wall, and this is the fiber angle, this angle of the cellulose fiber in the cell wall. And when this fiber angle is like this, like 50 degrees or so, the wood is very flexible. When the fiber angle is very small, the wood is very stiff. And then it breaks easily. It is strong in tension, but then it breaks easily. So the tree constantly changes this fiber angle depending on the load history. And Frank Rinn, a great scientist from the United States, found out when there's a tree in the vegetation period, so while everything is working, let's say in summer, and you take away a neighboring tree, within 6 hours, the cambium changes the fiber angle of the next cell wall that is produced. That means within 6 hours, the cambium is able to adapt the new cell wall, the next one, to better adapt to the higher load. There was a question in the back.
If you look at this angle, it's would dissect the tree. This would be the left side, or is it both sides angled like this, or are they angled like this? You understand?
No. I'm a physicist, you know.
This picture you have is if it's a cross section, it would be the left side of the tree.
I know what you mean. I know what you mean. I know what you mean. You know, the fiber angle is locally adapted to the need. That means on one side of the tree, you can have a completely different fiber angle than on the other side of the tree. And the tree does it constantly. And this is an example of a horizontal branch. And at the same time, on the top side of the branch, the tree builds wood with red marked, so color red, for low fiber angle. That means extreme high stiff wood. And at the same time, on the lower side of the branch, the tree builds wood with a very high fiber angle, with typically more lignin that has a higher compression strength, but a lower tension strength. So constantly the cambium in each cell decides what kind of mixture of density, that means number of lignin molecules built, and fiber angle is optimum for compensating the load. And as a general rule of thumb, typically trees compensate additional static loads, so constant loads, with a higher density. When this is not enough, they change the fiber angle. And dynamic loads typically are compensated by bigger tree rings with normal average wood. That means typically when trees are, let's say, suddenly they lose their neighboring tree and they have more wind load, the first compensation is building more cells with normal wood quality. If this is not sufficient, then in addition, they will change the lignin content. That means they will increase the compression strength on the compression side, and they will lower the fiber angle on the tension side. And if this is not enough, then they combine all these three parameters together. But it all takes more energy, and because of that, the cambium obviously differentiates. This is not related to compression wood and tension wood. Please don't mix that. This is a consequence, let's say, reaction wood. Conifer trees, when they are growing on a slope, as you know, they need to pump up the stem to come to the line. And this is done by compression wood cells. Compression wood cells are cells that, when they mature, they extend in the lateral direction. That means they get bigger and longer. And this is the stem to come up. Let's say, yeah, you have a conifer tree standing on a slope, and then this curvature comes by cells down here that pump up the stem. And in diffuse border trees, in broadleaf trees, they have tension wood on the top side where they have cells that shrink and pump up the stem with this way. Yeah? So the reaction to additional loads by wind or, let's say, clear cutting around is something different compared to compression wood and tension wood. But as I mentioned, it would take a week to explain all this in detail. So let's do that tonight at a beer. Here. I just lost the carrot. I wanted to explain with these two. So SIA calculates trees as if they would be built like a carrot. Carrot is very homogeneous, as you know. And the behavior under bending loads is totally simple. You can exactly calculate how this bends under bending loads. In a banana like this is much more like a tree. And the first thing that happens when you overload it is not that it cracks in this, but it cracks horizontally. It splits up. And this is what happens with trees. And this you can't predict because the material properties are so difficult, as shown by these colored graphs, these ones. There is not yet any mathematics available to cover that. It's so complex. You would have to take the tree apart in 10,000 pieces, measure all the parameters, put it back together as a tree, and then you can estimate probably with a factor of 10 precision. So just forget it. Yeah? Ignore it. Doesn't make sense. So we need just another method, very simple. So that means we need to, another aspect, which is important. I would like to mention that. I'm not sure if you are aware of, is anyone knowing Lynn Body? Yeah? Okay, that's great. Some people know Lynn Body. Lynn Body is a British scientist, and she did a publication in 1983. From my point of view, so important, but interestingly, usually not shown, and not trained, and not shown, and not discussed in conferences. I think you all know Scheigo. Yeah, we talked about that. Several people of you met him already. Scheigo often tried to say topping is bad. Do you know why topping is bad? Why did Scheigo say topping of trees is bad? It creates big cuts. Yeah?
And it makes the tree more stiff, less flexible.
Yeah, that's right. That's an important aspect. When you take away a lot of the crown is more stiff. The remaining parts are more stiff. That's right, yeah. Less damping in the crown, what Ken James showed very nicely in his studies 20 years ago already. Yeah, that's right. Another?
You took the dynamic out of the tree?
Yeah, you take the dynamics out of the tree. One aspect, you have another idea?
The branch attachment of the new twigs is very weak.
Yeah, branch attachments of new trees is very weak, that's right. And you have big cuts in the crown with often a lot of decay that comes up. But one aspect that was interesting, Scheigo mentioned this aspect often in his lectures, but he did not write it down clearly in the book. And this aspect was taken into account by Lynn Body and Rainier, and they clearly showed, I hope I have the summary of it. Let me check. Yep, here we are. So basically it says the moisture content in the tree is more important than any barrier zone. All fungi, like Ganoderma, Ustulina, Kretschmaria, however you call them, all the hyphae of these fungi are not able to penetrate cells that are filled with water. But what brings water into cells? It's the crown. The amount of wood in a defective cross-section that is filled with water depends on the number of leaves in the crown. When you take away 1/3 because you think, oh, down there is a defect, I have to take away, let's say, 1/3 of the crown to reduce the wind load, then approximately 1/3 of the intact part of the cross-section falls dry because the water is not anymore sucked through these cells by the leaves. And then these cells are falling dry, and then the fungal hyphae can enter these cells. Yeah, so that means water in the cells keeps the fungus away. Yeah? An apple a day keeps the doctor away. Water in the cells keeps the fungus away. And Linbody showed that 1983, the result of that publication is we should leave as much foliage as possible at the old trees. We should not preemptively prune down because we are scared that the tree is potentially dangerous. That means we should establish methods and rules that allow us to keep old trees as big as possible. That's shown here, and it is published 1983. And when I calculate correctly, this is nearly 40 years ago. Yeah?
Well, we're talking about tree topping, but is the parameter the topping of the tree or the removal of foliage?
The removal of foliage. And Shaigo said 1976 already. I was not present in that lecture, but he showed it. I just met one who said, Shaigo mentioned we should keep as much foliage in the tree and not top the trees because we need water in the cells to keep the fungi out. So he was aware about that. But unfortunately, he didn't write it clearly down in his books. But he was aware about that fact. And Linbody did, I think it was probably her PhD study to work on that. And she clearly showed we can keep the fungus how is it called, contained in that area where they are when we have a lot of water in the cells. So it's important to have a reason to argue when there is a tree with an obvious defect not to prune away the crown, just because this keeps the fungus stopping. Because in the early 1990s, the common procedure in many countries was, as soon there is an obvious defect, a defect that you can clearly see with your eye, without any technology even, when there is an obvious defect, first of all, take away 1/3 of the crown to reduce the potential risk of wind breakage or uprooting, which is understandable, but unfortunately, this accelerates the spread of the decay. Yeah? So that means we need to find a way to keep as much foliage as possible at the tree, although there is an obvious defect. And for evaluating this, we need a method that is based on science and not based on, no, I don't take the word, I probably should not do that. We have to avoid, and this is one of the aspects, absolute numbers. We need to step back a bit, and we need to be honest and say, we will never be able to calculate a tree correctly except we break it until it really breaks. And this was found, that was quite nice, by a group of experts in Germany about 15 years ago. They said, okay, we would like to check VTA and SIA if they are good in evaluating trees, and the only way to do it is to load the tree until breakage. And this is what was done. They inspect the trees with any kind of technology available on the market. Sometimes 50 people inspected the tree and drilled it and did tomography with any kind of device. So all manufacturers had been invited. And everyone was allowed to apply any kind of technology, and then everyone had to give an estimate. What is the strength? Which wind load will bring down the tree, so which pulling load will bring down the tree, and then the trees were pulled down to failure until the cracks were done. And the tree either uprooted or broken the stem. So we had both. And the main result was, the more technology we applied, the better our estimates had been, but they had never been precise. And this shows it is impossible to be precise at the tree. So we need to find a better way to let's say, to calculate. Somehow we calculate, but we have to calculate in a completely different kind of mathematical structure. And so that means, first of all, we have to study the science, and there's a lot of science out there. And if you're interested, I can give you a download link for about, it's probably 20, 30 publications that explain biomechanics. And interestingly, these scientists started publishing about that field in the 1980s already. And some papers we found that were important are from 1960. And interestingly, they were well known in the science, but they were not known in arboriculture. They were just ignored by the arboricultural world. So we have to acknowledge that every tree is different, every site is different. In the US, in the ISA meetings, we had a rule: for every ringtone, you donate $5 in the case. Sorry, I didn't know who was it. Okay, so every tree is different. The material properties are different, as I showed you by these colored pictures. Yeah? The material properties, this can be different in any tree. The typical structures is the same, but the concrete values that you find can be different in every tree. So every tree is different, every defect is different. Like when you go to a doctor, you get your result. When you go to 10 doctors, you get 11 results. Yeah? So, and probably when 5 people go to a doctor, it's 5 different results, although they have the same problem. So again, we have to be honest, it's so difficult that we should step back from absolute values. And absolute values, what that means, I will show you quickly afterwards. But before that, we have to find out who knows the wind load the best. The tree, because he can't run away. And we know that the tree constantly adapts the material property and the number of cells for compensating the wind load. That means, and that's the first step to understand, an intact cross-section of a tree is the reference, what is sufficient for compensating the wind load. When you are standing in front of a tree and you see there is an intact stem, this intact stem is the response of the tree to the wind load he faces every day, because the tree can't move away. When you see a tree that has a defect, and in the stem there is still an intact cross-section, we found a way to compare the defective cross-section with the intact cross-section and to evaluate if the defective cross-section is more dangerous or less dangerous than the intact cross-section. And then the next point comes into place, what is really important, at least in Germany. We had a clear decision of the Supreme Court in 1965. And the Supreme Court said, in order to guarantee traffic safety, that's the general term, traffic safety, the owner of a tree is responsible for the tree to be safe, and if he is not capable of inspecting the tree, he has to order someone, and the guy who is checking the tree and evaluating if the tree is safe or not has to evaluate if the tree, because of a defect, is more susceptible to be breaking or uprooting compared to the normal situation. The normal situation means compared to the intact situation. That means the Supreme Court decision does not say we have to scientifically study the material property, we have to scientifically measure strength values, we don't have to scientifically evaluate the wind load because it's practically impossible, and then to calculate absolute numbers of safety. We just need to know if the defective tree, because of a defect, let's say a car bumped against the tree 20 years ago and now there is a defect, if this defect makes the tree more susceptible to break than the intact cross-section of the same tree. Yeah, that means we evaluate, and I will show you some examples of pictures just of some trees to show you what I'm talking about. The typical tree with defects at the stem base because a car bumped against it. Yeah? You find that all over the world. Millions of trees are like that. So, but in many of these trees, we still have an intact cross-section. This is in Heidelberg, this is in San Francisco, this is in Perth, Australia, this is in Seattle in the state of Washington, this is in, I think, Madrid, and this probably is in Moscow, I'm not sure exactly. But I just took pictures when I'm traveling. So we find the same kind of defects everywhere. And just like, let's say this example, obvious defect, so do we have to do something? In many countries for a long time it was obvious when there is an obvious defect you have to reduce at least the crown. But what happens? When you reduce the crown, a lot of the cross-sectional cells fall dry. That means by reducing the crown, you accelerate the spread of the fungus. That means you squeeze the tree in a downward spiral that is expensive because you have to revisit the tree, and then you have to reduce again, and then this spreads again. You have more fungal fruiting bodies. That means basically doing this because we are scared about the tree, we reduce the crown, we increase the problem and make it more expensive. So it's crazy somehow. Yep.
Is there a certain percentage of crown that you can take out without reducing the percentage of water in the tree?
The question is if there is a certain percentage that we can take out without drying out. There is no general answer to that, I'm sorry. It depends on so many factors. Sometimes, for example, it's okay when the crown is non-symmetric to take away the parts that are reaching too far out. That creates a lot of torsional moment, because that's the highest potential danger to trees, because the torsional strength is the weakest property of wood compared to compression and tension strength. And when this is not very big, not a very big branch, and doesn't take a lot of leaves out, that's typically is okay. But there's no general answer to that. You have to check that. And actually you can evaluate this only when you know the internal situation. Either when it's opened, you can use a stick to check. If it's not open, then you need to drill or do a tomography. Otherwise, it's impossible to judge that, to evaluate if it's okay to take this away. But most of the time, interestingly, when we apply this concept that we developed, there is no need to prune anything. So we are doing this since about 15 years, and surprisingly, in most cases, there's no need to do anything. The concept, the mathematical concept, is to compare the defective cross-section with the intact, and it's practically simple. I just showed it in the break. As I mentioned, we cannot calculate the wind load. It's so difficult. So, but the wind load is the same for this, for that. The change is only that the lever arm to the crown is longer down here than it is up here. So that means the only difference between these two cross-sections in wind loading is the force to the crown is the same, just the length of the lever arm is different. The material property down here, the wood that the tree builds in compensating a defect, typically has a higher material property than these ones up here, because the tree down here reacts to a defect. So that means when we compare these two cross-sections, the assumption is the material property, the wood strength down here, is at least at the same level as up here, so we can ignore it. The wind load is the same to the crown for both, just the lever arm is different, and the consequence is there's a very simple way to evaluate if this lower cross-section is defective, is dangerous. You need to put in the height of the defect above ground, the diameter, the maximum diameter of the cross-section. The diameter represents the response of the tree to the defect. And because the diameter goes to the power of 3 in the load carrying capacity, even an increase in 1% increases the strength, the load carrying capacity, by 3%. That means when the tree starts compensating and makes the stem bigger, it's the response for compensating strength loss due to the defect. And when we measure the maximum diameter and then the same direction, the diameter in the intact cross-section, we know that this is the response of the tree to the defect. And by putting in the maximum diameter of the defective and the diameter in the same direction of the intact cross-section, 5 numbers, and the total height of the tree, this application shows you what the safety factor of that cross-section is. Taking into account, don't forget your question, that this cross-sectional sketch here shows you that this cross-section lost about nearly 30% of load carrying capacity compared to the fully intact cross-section. And again, this concept is trying to get rid of all the complex stuff by assuming, being on the safe side, that the material property of the wood down here is at least as strong as the strength up here. Typically, it's the opposite. Typically, this is much stronger than up here. And in addition, the lever arm from down here and here is calculated approximately to the center of the crown. So assumptions that show that in reality the tree is even safer than this calculation shows. But I just wanted to show that just general idea. We tried to get rid of any kind of absolute value. When you go this way, you don't need to determine the wind load, because the wind load to these two cross-sections is the same, except for the lever arm. And we just compare these defective with the intact cross-section, because we don't need to determine the absolute value. We just need to know if the defective cross-section is safer or unsafer than the intact cross-section. And when it's safer, you can go home. why should you prune the crown, although there is an obvious defect, when the defective cross-section is safer against breaking than the intact cross-section? Because when you don't believe the intact cross-section to be safe enough, you would have to cut down every tree. Yeah? So that means this is a completely different approach, because we are using the intact cross-section of a tree as the measure for the wind load. This is implicitly used by that. And we compare defects always with intact cross-sections. There was a question, I'm sorry, I was skipped. Yeah.
You only use examples of old defects which already have reaction with.
Yes, no fresh defects.
How do you handle new defects which do not have the reaction wood yet?
I have no idea yet. I have not yet.
Reaction wood increases, so when
I know. I have some ideas to solve that for fresh defects, you know, when you currently take away 1/3 of the cross-section. And this application on the right shows how much percent is lost in terms of load carrying capacity. But this then would require to, we could, percentage-wise, we could determine how much we would need to reduce the crown in order to compensate for the strength loss. But then we would need to try to keep fungi out of that defect, because then it would be a problem, yeah. But for a fresh defect, it's not a solution yet. Yeah, probably next year I have one. We'll see. Okay, so this is a solution for trees that have still an intact cross-section to compare with. Yeah. Oh, there's one and there's another one. Oh, there are two. Let's start there.
Frank, do you deduct the volume of the defect in this?
In this case, I just did 2 resistance drillings, and then I did the sketch. So, and when it's open, I just use a stick and just sketch it by hand. And if the tree is important, I do a tomography. But it always depends on the owner of the tree if he's willing to pay more. You know, this application, when the cavity is open, then typically it takes a minute for one tree. So this is really cheap. And okay. And when the tree is more important, then I say, okay, then I need to drill, then it's more expensive. And when the owner says, okay, go for it, then I do it. So it depends on the contract. So there was one question there, and then you. Yep.
Ja, maybe someone can translate it. Wij hebben in Nederland sinds een paar jaar de richtlijn takbreuk populieren. En die geeft aan, als je uitzakkende takken in een kroon hebt, die dus een grote gat maken in de kroon, dat je die tak dan met veteranensnoei wat kan innemen. En zeg jij niet doen, dat is die kan dat even gedaan.
Well, he's asking a question about large pepper trees that have, due to age, deformation in big branches.
Yeah.
And the
Okay.
question was, the guidelines tell us to do reduction pruning.
The length of the branches, because they are deforming.
They are deforming and have a higher chance
Of breaking, yeah.
And the guidelines tell us to do reduction pruning.
Yeah. You know, reduction pruning is not a problem as long as there's not a big defect at the stem base. When there is a big defect with only small shell walls, then it's a problem, because then this correlation between the foliage in the crown and the amount of water in the stem is strong. When the tree is still fine at the stem base, then reduction pruning is not a problem. It's only a problem when there is a big defect in the stem, where you want to keep water in the remaining parts of the wood to keep the fungus from expanding. Yeah. So there was another. Yeah. Is that an answer? Okay. Good. You had a question.
My question is that a lot of damage at the base of the stem
Yeah.
is also compared with fungal infection.
Like here, there's always a fungus. It's always a fungus. There's no other deterioration of wood except for a bacteria underwater.
But like Ganoderma does the most damage from the ground level to
Yeah.
base 40. How do you take that into account? Because we know that somewhere it ends and then the roots are hot and then the tree comes over in storm.
Yeah, at the beginning of my lecture, I skipped that. I had two statistics, one from Germany and one from Singapore, where they showed that approximately 70% of the accidents reported to the police and official municipalities come from the crown, about 10% by breaking stems and 20% by uprooting trees. So for sure, the problem down there is much bigger than the one in the stem. But I'm talking today only about the stem breakage, thanks, because the other thing is more complex and I would need another day for that. So that's all. But very valid question. There was another one I missed. I don't remember exactly where it was. Okay. So what happens when the tree has no intact cross-section anymore to compare with? Here we are. So these are typical trees, veteran trees. In the middle, this is Ted Green. Do you know Ted Green? Yeah? Crazy guy. He's wonderful. He knows all these trees in Windsor, and he's standing in one of these old oak trees. There are many veteran trees where this concept with the comparison of an intact cross-section doesn't work, so we need something else. And I'll just show you one example of a typical calculation for that. This tree, an old tilia tree standing close to our office, has a strong defect in the stem, in this case drawn by hand, so just based on a few drillings, for example. And the strength loss is about 24%. It lost some roots for sure in addition. What has to be taken into account in this cross-section, the stem is completely rotten to the top, so there is no intact cross-section to compare with. But the tree is about 100 years old, and since about 30 years, this tree is not anymore growing in height, because most of our typical urban street trees, they reach the maximum height with about 60, 70, 80 years old. So our tilia trees in our region, typically with 70 years age, they have reached their maximum height. But what happens when they are still alive? Like when we get older, we put on new tree rings every year. That means the trees get bigger and bigger and bigger, and 1% increase in diameter means 3% increase in load carrying capacity. That means when a tree is 100 years old, since 30 years, every year he gets a bit bigger. That means he got significantly stronger, and this explains why these old rotten trees, like in Florida and Miami, or the big sequoia trees, why they are completely hollow, but still strong enough. Because obviously, like in Florida, that's a nice example, the young intact trees have a safety of, let's say, 1 or 100%. That's their basic natural safety factor, but they can snap in a storm. But these old trees, as you saw in these examples that I showed you, they are completely hollow, but still are stronger, safer than the young intact trees. That means their safety is more than 100%, because, as I said, and as I showed you here, this tree is about 100 years old. That means since 30 years, every year the tree rings get bigger, so that the stem gets bigger. That means when in these 30 years, the tree got bigger by 10%, the load carrying capacity increased by 30%. But the wind load didn't increase because the wind load depends on the height of the tree. That means when trees get older, annually, they get safer, just by aging. Aging means in trees, as long as they are alive, they put on new tree rings, even a small one, they get bigger and bigger and bigger and safer. That means the older trees are, the bigger the defect is that they can tolerate without being dangerous. That means the percentage, if it's dangerous or not, depends on the age of the tree. The percentage alone tells you nothing about the tree, if it's safe or not. For a young tree, 24% strength loss is dangerous. For an old tree, it's nothing. Yeah, that means the age is important, so age really matters. In addition, this tree originally had a height of 25 meters, and now it's 20. That means it lost about 5 meters in height. So when you take into account these two aspects, this increases the safety so that although it has a significant defect in the stem, this tree has a safety level of more than 200%. That means it is safer than the same tree was when it was intact. And this tree is the one that knows its wind load the best, so I'm comparing the tree with itself, because no one knows the wind load better on that side like the tree itself. Yeah, that means we compare the tree with itself in the past when it was intact. And the major aspects in this case are reduction of the crown that had happened because of pruning. And the other aspect is the aging. That means the older the trees are, the higher the compensation effect by the age. And that means the older the trees are, the more defects they can tolerate without being dangerous. And this explains why these old trees in Miami, for example, are completely hollow, but they survive storms with 250 kilometers per hour, where a normal intact tree would snap. And this is exactly what happens. So that means this method is confirmed by nature, yeah, because it explains what we find in nature. So this is the way how we try to hopefully replace VTA and SIA in the future. We call this concept allometric self-referencing. Yeah, allometric because it refers to the allometry, that means the sizes and shapes of the tree, and compares it with itself. And this is why it's called allometric self-referencing. So, summary, the VTA thresholds are not wrong, but just don't apply to these urban trees. The SIL calculation is fundamentally wrong. So that means we need something else. And I think with this kind of allometric self-referencing, we have a method that should be practically used. I don't know how long it will take for the old methods to step down. So I think it makes sense to go this way. So I encourage you to to check that. Even George Bush learned in the last year of his presidency that tree rings tell you something about climate, and he immediately invited Angela Merkel to explain it to her. I don't really remember who knows more about that, I assume something. There was a question if I could talk something about crown cabling, and I will use the last 2 minutes about that. In the German standard, we had, you had the question?
Yeah, about the method.
Sorry, about?
About the method you were...
Yeah, the self-referencing. Yeah.
To avoid future misuse of the method, like it happened to VTA.
Yeah.
What specifically, could you explain what specifically it can be used for, and which type of situation? Like, because you're mentioning it has to be maybe an old decay.
I think the example that I showed, as long as you have an intact cross-section of the tree, perfect, it works well. And when you have an old tree where there is no intact cross-section to compare with, it works well as well. This does not yet cover root, because that stuff is more complex. I didn't explain what we do in this case. Just send me an email. I will send you some material to read on. You know, it's difficult in these 2 short lectures to cover a topic that would normally take a week to explain. So because of that, I'm just jumping a bit from point to point. So I'm sorry, I can't explain everything in detail. But I'm happy to do it afterwards. But it will take a week, as I said. So basically, in our German standard, we defined 3 kinds of cabling: a dynamic, a static, and a holding. And I don't go into the detail, but I just would like to show one major argument. The dynamic cable, by definition, should be put in on 2/3 height. Yeah, that's the definition in the standard. 2/3 height of the limb, there should be the dynamic cabling. And you see how it's put in. There is no slack. Yeah, the cables are straight. It's completely wrong. As Ken James clearly showed, you have huge movements of these branches within the crown in the storm, and they are uncoordinated. And this is just an example, measured values. You have a platanus tree, and on 2/3 height, the distance was about 3 meters standard on 2/3 height between the 2 limbs. In the storm, the distance in maximum was about 5 meters, sometimes nearly 6 meters. So to cover that would need your rope looking like that. No one does it. In consequence, typically the ropes are too tight, increasing the wind load to the stem head. We have significantly more damages and breakages in trees with these dynamic crown cablings. But since it was introduced in the German standard since 1994, the major companies sold 20 million systems. So 20 million systems, when you assume €100 per system, that's 2 billion euro. That's a bit of money. And it doesn't make any sense. It was introduced, and it was reintroduced again in 2017 in the German standard, just to prevent people from topping trees. So it was basically a psychological thing to keep people away from topping trees. That was the main idea behind it. So technically it doesn't make any sense. Until today there is no single publication showing that it really works, because it can't. The only thing that really works is a static cabling. Another aspect that happened, a lot of people started strangling trees with ropes and belts, because they didn't want to drill, because drilling is bad. But this basically kills trees, as you can see here. When you want to keep trees with these belts, basically there's no flux through the phloem anymore, and you kill the roots, and that basically kills the trees. This happens to thousands of trees in these climbing parks in the forest, in zipline courses, unfortunately. So some German arborists use this kind of static cables at the base to prevent a cracked fork from falling apart, and this works fine. It can be readjusted, looks like this, and then you don't infringe with the dynamic movement in the top. That works well. But as I said, this is a long talk as well, so it would take another few hours to explain that. So the dynamic cabling doesn't make any sense. It doesn't work physically. Practically, it increases the amount of accidents that we have by trees, so we should not use it anymore. And the static cabling systems should be done down there and not on top, because Ken James clearly showed we need the dynamic movement of the branches up there. We can prevent that they fall apart down there, but we should not do it up there. There was a question?
Most tree on the right.
The holding and catching system, yeah.
You reduce the branch for about 20%.
You don't need to do that. You don't need to do that anymore, yeah. This is used in Germany when the branch already cracked. It's opened and cracked. Then this is used. Yeah. Okay. Let's stop with this picture. And I hope I didn't bother you too much with my bad English. As I mentioned, you will be provided the presentation, so you can recheck that online. And if you have questions, just contact us. And yeah, thank you for your attention. Thanks.
Thanks. I like the example of the banana and the carrot. The presentation will be available on YouTube as well. It's a lot of pictures and a lot of information. So thanks very much for a lot of new information for many people, including myself.